Okay, so that's a shift. Okay, so we've looked at all the shifts now. So it can either happen horizontally, in other words, left and right. And if that happens, you need to change the value of x. But if you change the value of x by like adding or subtracting in some value, well, it's the opposite of what you think it should be. So if it's like plus 2 here, it'll actually be 2 left. Okay, and if it was like negative 5 there, it would actually be 5 right. Okay, if you wanted to change it in the y direction, so moving up and down, then you do your function first, then you change the value, and that's okay. That's exactly the same as what it should be. So if you do like x squared, then plus the 3, that means move it 3 up. If it's like take away 10, we move 10 down, okay? So good, all right. The other type of transformation that we need to look at, so there's 2 others, is something called a stretch, okay? So a stretch literally just means I take my graph, grab hold of it, and I basically pull it outwards, or pull it up and down, and pull it out left and right, okay? So let's first of all look at this one, okay? Let's do f of, let's do f of x first. Let's put our value through the function, and then let's change it by 2. So let's multiply everything by 2. So stretches are all to do with multiplication. Shifts are all to do with additional subtraction, okay? So in this case, because my function is x squared, I'm basically going to take x squared and times it by 2. Does that make sense? Okay. So same thing as before then. All I want you to do is just tell me what value I get out in each of these cases. So let's start off with the easy one. Let's start off with 0. What value would I get out if I stick it in this function? If I stick 0 in this function, what do I get out?
0.
Good. If I stick 1 in this function, what do I get out? 2. If I stick 2 in this function, what do I get out?
8.
Good. If I stick 3 in this function, what do I get out?
18.
Excellent. And if I stick negative 1 in this function? Good. Negative 2?
8.
Excellent. And 18. Good. So that's the line of symmetry. You found the line of symmetry here. Okay, good. Fantastic. So let's have a look at this then. Let's try and plot it. So you basically get a graph that looks something a bit like this. Okay, so the vertex is still fixed. We haven't changed the vertex at all. It's still going to be at 0, 0. Okay. However, how would you describe the transformation? What's happened to get from here to here?
Thinner.
It's thinner, yeah, absolutely. So, I mean, the way which I want you to think of this, it's almost like somebody's literally grabbed this graph and pulled it upwards, okay? So it's now skinnier, right? It's now every y value is twice as far above the x-axis as it was before, okay? So the way which I describe that is using a stretch. Somebody's literally grabbed hold of it and pulled it upwards, so they've stretched it, okay? So I'd say it's a stretch. Which direction is it happening in? X or Y direction? Y direction. Somebody's literally pulling it upwards. So it's happening in the Y direction. Now, what's the scale factor? So the scale factor is literally how much they're stretching it by. Two. Fantastic. Look at that. 9 becomes 18, 4 becomes 8, 1 becomes 2, 0 becomes 0, 1 becomes 2, 4 becomes 8, 9 becomes 18. It's literally making everything twice as big as it was before. Therefore, the scale factor is 2. Okay? Okay, that makes sense then. So basically, if you take your function, put your value through your function first, and then you multiply it by 2, that will correspond to a stretch by a scale, in the y direction by a scale factor of 2. Okay? So it's happening in the y direction because it's happening after you've applied your function. Similarly here, if you change the value after you've applied your function to it, it's happening in the y direction. Okay? All right, let's change it then. Instead of doing the 2 after we've applied the function, let's change the x value first and then apply the function. So let's do f of 2x. Okay? So let's do f of 2x. In other words, we change the x value first, then we apply the function through it. So in this case, we're basically saying change the x value, so 2 times x, and then square it. Okay. So can you tell me what to get out? So if we put 0 in, what do we get out?
0.
Good. If we put 1 in.
4.
Good. If we put 2 in.
16.
Yep. If we put 3 in.
36.
So 3 times 2 is 6, so that's 36. Perfect. What happens if we put negative 1 in?
It's the same.
So negative 2 squared, so that's 4. Okay, so what if we put negative 2 in? 16. Perfect. So you've noticed the line of symmetry again stays fixed. Okay, so for the x value, line of symmetry lays fixed. Okay, so in other words, we get something that looks a bit like this. Okay, so we do a graph that looks a bit like this. So the vertex stays fixed at 0, 0. Now it's still a stretch in the x direction because we're changing the x values. We're changing the input value, so it's still happening in the x direction. So it's a stretch in the x direction. However, okay, what's the scale factor? So literally what I want you to think of is that somebody's taken this original graph, they've grabbed hold of it, instead of doing it in the y direction, they're doing it in the x direction instead. So it's kind of like they're doing that instead. Okay, they're pulling it outwards and inwards. But what's the scale factor? It's not a scale factor of 2. And here's the reason why. Okay, if somebody takes this graph and makes it a scale factor of 2, they're literally pulling it outwards in that direction, so it's twice as far away from the y-axis than it was before. But does that look as if it's been kind of made flatter? No, it looks as if it's been made skinnier, hasn't it? So it's almost as if somebody's taken it in and kind of pushed it inwards instead of pulling it outwards. So instead of it being a scale factor of 2, in other words, every x value is twice as far away from the y-axis than it was before, what's actually happened is the other direction. They've pushed it inwards, so it's now half the distance it was before. Sorry?
Divide.
Perfect. It's been divided by 2. Okay. Now the way which I'm going to write that is a half. Okay, because it happened that's still divided by 2. Okay. So that's really weird, isn't it? So similar kind of thing. There's always something fishy going on with the x values, the x sort of transformations. Y transformations behave. X transformations, they kind of do something fishy. You're looking at that and thinking, oh, okay, it's happening in the x direction. Scale factor of, hang on a minute, half? What? So it's just basically saying, well, you take that 2 and you're dividing by 2 instead, and then it becomes a half. Perfect, well done. Let's generalize them. Okay, so we just said, let's do the y value because we did that one first. If we take some constant, let's say b, and we times it by f of x, okay, so literally like we're doing here. We just said that's a stretch in the y direction, so I'll say in y direction. But we said that the scale factor, so I'm going to write SF as a shortcut for scale factor. And the scale factor in this case will just be b. Okay, so whatever we multiply the f of x value by, it will basically be made, the y direction will just basically be pulled up that many times in the b direction. Okay, so as an example, we might have 2 times x squared. Whereas when it was happening in the x direction, so in other words, we did the b times the x first, then we applied the function, so f of b times x, that's still going to be a stretch, so it's still a stretch. Well, we're happy it's in the x direction because you're changing the value of x first. So stretch in the x direction. Okay, but this time the scale factor, so I'll write SF for short, is not going to be b. So it's not going to be basically pulled outwards by b units. It's going to be pushed inwards by b units. So it's going to be a scale factor of 1 divided by b. So it's going to be dividing by b instead. So 1 over b. So as an example, you change the x values to do the 2x, then you do the squaring.